We're on Module 12. So we're going to be, this used to be Module 2, y'all, back in the old book. So this is when you say, yay. That means the stuff in here is not going to be all this heavy-duty kind of stuff, okay? So it does, everything we've learned, we build on it here, but I don't even think I mentioned the word stoichiometry today. Yay. All right? So we're kind of getting back to some basic things that are going on right here. Okay, and, no. There we go. All right, so I'm just going to play this little video, and I've just put this in here. It's got nothing to do with anything. Well, it's got a little bit to do with what we're learning about today. It does have to do with chemistry. But I put this in here to remind you that chemistry is really awesome, even though our last couple of labs have been kind of lame. So sorry about that. Yeah, it's kind of the limitations we have coming once a week, and there she is. And also that as far as the danger aspect goes. Okay, like you're going to see some of the stuff in the video right now that you'll see why we can't do that here. Okay? If I had a hood, this hood with this exhaust that takes the stuff, we could burn stuff, we could do all this cool stuff. We don't have that. And I'll tell you that a lot of the high schools don't have that anymore anyway. And the reason is liability. They've had students get hurt. And so there's less and less of that happening in regular schools. A lot of it's done virtually, that kind of thing. So we do what we can to try to illustrate what chemistry can be about. But let's just watch this little fun thing. This one we know. We did this one. Not quite such a big beaker. Do have that traffic light one, so we'll be doing in a future lab right there. So, all right, so just to remind you, remember chemistry is really, really fun, really exciting, okay, all right. And furthermore, if you want a job and you get a chemistry degree, you will get a job, promise. Everybody needs a chemist, okay? All right, so today we're talking about heat transfer. We're talking about energy and heat transfer. So one thing you need to know is that heat always transfers from a warmer object to a cooler object every time, okay? And it has to do with something called thermodynamics, okay? And how thermodynamics is causing there to change. We're going to have a whole module on thermodynamics, and it gets kind of complicated. We have weird words like enthalpy and entropy and all those things that we'll bring into that. But we're working up to that. So this is going to kind of lay the foundation for that, understanding how heat and energy are related to each other. All right, so we're going to be transferring heat from a warm object to a cooler object. All right, so energy, what is the definition we'll be using? It's the ability to do work. But now we have to define work. So work is the force applied to an object times the distance that the object travels parallel to the force. If you want to write that in a smaller amount of words, you can say work is when something is moved. Something gets moved. If I move something, I move this, work has been done, okay? There is a mathematical equation to go with that, however, so you can write that down as well. So here it is. In order for work to be achieved, objects must move, motion must happen, and here it is. Work equals force times distance. Work equals force times distance, which is all that sentence is saying right there. That's all it's saying, is that we have that little mathematical thing, W equals F times D. Not difficult math at all. All right? We got those blanks filled in? So today we'll be looking at motion happening. So if you think about heat, if you're sitting in front of a fireplace and you feel the heat, guess what? It's moving towards you. That heat is moving towards you. So work is being done there. So energy is being utilized. All right. So energy, heat is specifically energy that's transferred as a consequence of temperature differences or energy moving from a hot body to a cold body. All right. So I think those are your blanks there. And it's always going to go that way. So my hot coffee is always going to cool down. All right, I've got it in my cool, insulated mug over here so it doesn't cool down for a long time. It's too hot to drink, in fact, right now. So we've got some technologies, right? In fact, we're going to, next time we get together, which is 2 weeks from now, we're going to be working with this cool little device called a calorimeter. I've got 2 of them, and then I thought I would use a Yeti cup as a third calorimeter and just compare it. I think a Yeti cup's going to be better than a calorimeter, honestly, because they insulate so beautifully. All right, so the way we figured this out, y'all, is to figure out the heat. We're going to measure heat using a thermometer. That sounds like, you're like, well, no, duh. Right, obviously we're going to use a thermometer to measure heat. But the thing is, it's not really measuring heat. It's a little bit of an illusion. And the deal is, what we're doing is we're measuring heat sort of to the side. Measuring actual heat is a difficult thing to do. So we're going to do it, we're going to do it indirectly, okay? So our thermometer is going to register the motion of molecules, okay? So our thermometer has a bulb with a liquid in it. In the old days, we used mercury. Mercury is a liquid metal. It's also toxic, and so we don't like to use it anymore because it has to go through a glass, and to get it to go down into its little bulb, you have to shake it really hard. Y'all don't even remember these days. When my kids were little, I'm like, and if you shake it too hard and hit something, you break it, and the mercury goes everywhere, and then you have a toxic spill in your home. And so we decided to not use mercury anymore, but what we're using is alcohol, and the alcohol's been colored red, and alcohol will respond to, it'll expand when molecules hit it faster. All right, so if the molecules start to move faster, they'll hit the red liquid, and it'll push it up this little skinny tube inside the glass tube of the thermometer. Okay, so that's an indirect measurement of doing that. So it gets pushed up there. Of course, we'll be using Celsius most of the time, Kelvin in certain calculations, right? Remember, we had to use Kelvin last time because we didn't ever want our number to be 0 or negative because it would mess the math up. But generally, we're going to be using our Celsius, and I think we'll be doing that today as well. Okay, so our first law of thermodynamics, everybody should know this. Anyone?
Energy can't be created or destroyed?
Energy is neither created nor destroyed. It only changes form. Very good. That's like the fundamental law of the universe, which baffles me that scientists can, in any kind of authority, say that life came from nothing, that creation came from nothing, because they all believe that energy cannot be created or destroyed, it only changes form. Every scientist believes that. And so for them to say that there was evolution is to defy this. It gets a little more complicated than that. They have a better argument than mine. Mine seems very plain, but at the bottom of it, I'm right. So there. God only made so much energy for the entire universe. Energy is finite. All right, there's only so much, and we have to keep switching back and forth with that energy, because we can't make it. You think, well, I'm burning a fire, and that's energy coming out of there. Yeah, but that energy was always there. It was always there. It was trapped in there. Here's our guy with his hot cocoa. Bob knew the laws of thermodynamics and heat transfer would hold true once again. His hot chocolate would soon be cool enough to drink. Okay, it's always going to be cooling down. All right, so types of energy we'll be looking at, like I said, my wood that I put in my fire, right there, it contains something called potential energy. It's stored energy that's in there. As soon as I light that wood, I will have energy that's in motion. That's the burning wood. That's called kinetic energy. Kinetic means movement. So then we see the difference here, but the energy was put in there in the beginning. Heat is considered kinetic energy because it's moving towards you. Okay, it's moving towards you. That you can feel that heat coming towards you. In fact, we also know that heat rises. Yeah, heat rises, and so that's moving, right? So it's going up. So if you have a two-story house, you may have noticed the upstairs is actually a little warmer than the downstairs because the heater keeps sending everything up there, right? So it's motion. That's moving. All right, here's our fire. There it is. Check it out. I don't know about y'all, but we had one of these back in the cold snap. Yeah, I had a fire and fireplace. It was very nice. And notice also the flames move, right? They really can't explain exactly why those flames move the way they do. Scientists always want mechanism for everything, and they don't really have a mechanism. I just think it's beautiful, and we can look at it and be mesmerized by the flames right there, you know. And of course, it's consuming that fuel there, typically, unless you have fake logs and gas in there. So our potential energy is stored energy that matter possesses because of its structure or its location. Chemical energy, for instance, in organic molecules, when I break something down, I'm breaking bonds of chemicals, and that creates energy. If we had been able to do our lab over the cold day, we would have done some exothermic reactions and endothermic reactions. We're still going to do those. I'm going to fit those in to one of our labs that's kind of, you know, I should have probably done it last time, right? But I have these cool little packs that heat up and cool down. Kinetic energy, of course, in motion. Here we have water gushing through a dam. That creates energy, spins a turbine. The turbine will spin a magnet. The magnet will make electricity, comes into our room. Yeah? Okay, so all that can be worked. We can use that work for our good. Activation energy, okay, there is, so you think, here's our wood sitting in the fire. And to go through combustion, we have our fuel. What other thing does combustion need as a chemical reaction? Somebody, oxygen, right? So is that wood surrounded by oxygen? Yeah. Why isn't it bursting into flame spontaneously? Because it has a high activation energy. Okay, and we'll get to this too in another module. The activation energy must be reached. So how do I activate that energy? I put some sort of flame. I light a match, or my husband uses like a propane torch and gets it under there, gets it going really good, you know, so I have no smoke in the house. That kind of thing to activate that energy level to get that reaction started. Same thing happens in chemical reactions. Of course, fire is a chemical reaction. All right, let's see. Is this? Okay, so think about this. There's potential energy in there. So what kind of energy is in an apple? Do y'all know? Sugar, yeah. It's actually fructose, which is C6H12O6, just like glucose. It's just structured a little differently, so it's sweeter to the taste. Here, oh yeah, is there energy there? Yeah, is that moving? Yeah, we have a burning furnace going on up in there. The sun, we think it's fusion between hydrogens fusing together to become helium and releasing a bunch of energy when that new molecule's made, or that new atom is made, actually. And we have our heat there. Here we have a bar of gold. Is there potential energy in gold? Absolutely. In fact, we use gold for some things, like some electronic things use gold, silver mostly, but gold. And then we have our fire right there, which obviously we have our potential energy in our wood and our movement in our fire right there. So these would be, at this point, considered potential energy. These would be considered kinetic energy, you know, because they're in their process of moving right there. Okay. Oh, let me see. I think I had another video. I think this is a video. No? All right. Well, we're going to watch this video then. Execution. Let's see. I'm not sure why it's not working. Well, now y'all are going to be upset if we can't watch an execution of a gummy bear. Oh, wait, there it went.
This video I'm going to demonstrate how much energy is contained in one gummy bear. What I have here is a calculation for how much energy in the gummy bear. On the pack it says 100 calories per 16 bears, which comes out to 6.25 calories per bear. Now, those are food calories, so you multiply that by 1,000 and you have 6,250 calories. Times by the conversion to get the joules, 4.18, and you get 26,125 joules, or roughly 26 kilojoules. And this is the energy I'm going to demonstrate.
Execution hour.
What I have here is a test tube of molten potassium chloride, KClO3, which is an oxidizer, and it's going to chemically burn the gummy bears. So a red gummy bear here, and let's see what happens when I drop this in. And you should do this outside.
I think he's in a hood, you know, got a hood there. We're not gonna do this one, y'all.
Okay, right there is the release of 6.25 calories. Let's throw another gummy bear in there. See what
Wow.
which is 26 kilojoules of energy, roughly what your body has to consume to get rid of one gummy bear.
To eat one gummy bear, you gotta have that much energy.
You ever wonder why kids are hyperactive?
Okay, that might be a fun, what do you call that? Science fair project. It could be done outside, right? In the dark. That'd be fun. All right, we're going to talk about this guy. His name is James Prescott Joule. We're going to talk about him because the unit we're going to be using for energy is a joule. In fact, the guy in the video just mentioned that, the joule. So it's named after him. Notice he says, order is manifestly maintained in the universe, governed by the sovereign will of God. He was absolutely a believer. Everything he studied confirmed his faith in God. And so people tend to sort of set that aside nowadays. But this guy was brilliant, right? So it wasn't just because he came so early that he didn't realize, he wasn't enlightened. No. In fact, I'll have his years on here in a second. It's like well past the Enlightenment era. It's in the late 1800s, I think. Yeah. All right. So the unit we're going to be used for measuring energy is called the joule. All right. And a joule is the amount of energy it takes to lift 102 grams up 1 meter. That's the official definition of what a joule is. The energy it takes to lift 102 grams up 1 meter. All right, here he is. Look, he was in 1818 to 1889, well past the Enlightenment time. So he still could have believed in something besides God, yeah? In order to measure energy, you must measure temperature change. Remember, we're indirectly getting this energy by measuring this temperature change. So we have something called a calorie. That's the amount of heat necessary to warm 1 gram of water 1 degree Celsius. This is different than the joule, right? This is to measure the calorie. And then in chemistry, a calorie is 4.184 joules. Do you have a place to write that one down? 1 calorie equals 4.184 joules. That equals 1.00 chemistry calorie. Now, the reason I say chemistry calorie, he mentioned that briefly in the deal, I think, yeah, that one food calorie equals 1,000 chemistry calories. And so typically when you see calories for food, if you're looking at a wrapper or something like that, the calorie will be in a large capital C for calorie. That means 1,000 chemistry calories, okay? So I think the reason they do that is because if we saw how many calories were really in food, the number would be too big to be on our little packages. You know, so I think there's like, 3,000 calories in a Big Mac. Yeah, but that's food calories. You have to multiply it by 1,000, so 300,000 calories in a Big Mac. Okay, so there's a lot of calories in there. Okay, so that's how we're going to be measuring. We're looking at calories as the amount of heat there, the chemistry calorie, and the unit will be in joules. So here's just a little picture. Okay, what is it? How much it takes for 1 kilogram of water to be warmed 1 degree Celsius will equal our calorie right there at sea level. Yeah, so has to be at sea level. Okay, so here's practical application. An average person uses 2,500 calories of energy per day. So how many joules is that? First, you convert to chemistry calories. 1 calorie equals 1,000. So 2,500 calories times 1,000 is 2.5 times 10 to the 6. We convert that to joules. Here's our 4.184. And that's going to be 10,460,000 joules per day. Sounds like a lot. All right, so that's going to be our, and here it shows different kinds of food, what kind of energy we get from some of these foods. Okay, so how much exercise does it take to burn off calories? So I'd have to have, I think this is joules. Is this joules? Yeah. standard chocolate bar, I need to have 229 joules of energy to burn that off. Is that right? Or maybe I need 42. That's what it is right here. If I'm running, oh, I have to run for 22 minutes just to burn off 1 calorie? Candy bar? Yikes. How about a sandwich? 42. Oh, an hour and 22 minutes of walking to burn off 1 sandwich. Wow. Our Coke doesn't seem so bad there, right? 13 minutes of running is all I need for that. Okay. All right, so measuring heat. In order to measure heat, we're going to use something called the energy equation. So there is some math this module, but it's not terrible. All right? So, and we're going to be looking at something called Q. Q is the amount of heat that is released or absorbed, okay? And looking at something known as specific heat. So now I believe we switch over to 12B. Okay, so we're looking at now something called Q, something called specific heat. And we're going to watch Professor Dave here explain a few things.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water, and the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water
100.
to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension.
Okay, we're not going to do that. We'll do that later if we want to. Okay, it's just a math problem. All right, so we're going to literally do that that experiment. We're going to heat up a metal, 100 degrees, put in thing, but we have to do those 2 steps. All right, we have to do it twice. All right, so joules or chemistry calories are used for measuring the amount of heat absorbed or released. 1 chemistry calorie is equal to 4.184 joules, and 1 food calorie is equal to 1,000 chemistry calories. So the chemistry calorie is the amount of heat necessary to warm 1 gram of water 1 degree Celsius. I'm repeating this here as if we're in second week. Okay, some review. Okay. All right, and so here's what you need to know. Now notice he used that little S for specific heat. We're using the little letter C, lowercase c for that in our book for whatever reason. So this is our equation this week that you must memorize. Q equals mc delta T. Q equals mc delta T. And what's interesting about that is that C will be given to you. It has to be given to you because it depends on what we're using. All right, this is what I was getting mixed up with last time. That's going to depend on the metal we're using, the substance we're using, whatever we're heating up. It's going to have its own specific heat. It'll be specific to the item, right? And then Q is going to be our energy, all right? And M is going to be the mass, and delta T is going to be the change in temperature. We're going to be measuring the change in temperature. That's our indirect observations. Okay, so Q is energy, M is mass, C is specific heat, temperature change, T final minus T initial. That makes sense, right? And then you have to remember, what am I doing? The delta T for what? For the water or for the metal? So just make sure you start with the proper in the proper place that you want. So, but that is the equation we'll be using. It's not difficult. And I think I have it. Again, do we need anything written on this one? Right there. And this one, what did it change? Nothing, right? So it's still called C specific heat right here. Where in his deal he called it S for some reason. All right, so if you want to rearrange them, here are the rearrangements. If you want to write those down for our algebra. We're looking for C, which is our specific heat, which is what we will be doing in lab, y'all. We're going to try to to calculate the specific heat so we can therefore look at a chart and see what metal it is that we've just been working with, okay? And we should be able to pin it down on some sort of chart there. Mass is interesting because we just measure mass, right? Maybe it's how much do we need for this amount of energy to be created, something like that. And our delta T, of course, is also collected during our experiment. All right, so what is exactly specific heat capacity? It's the amount of heat necessary to raise the temperature of 1 gram of substance by 1 degree Celsius. Everything is unique. The larger the specific heat, okay, this part I want you to listen to. The larger the specific heat, the harder it is to heat the substance. Okay, it's more difficult to heat the substance. The lower the specific heat, the easier it is to heat it up. So copper, for instance, has a specific heat of 0.3851, and aluminum has it 0.900. So copper is easier to heat up because its specific heat is lower. You get it? So the lower the specific heat, the easier it is to heat up. And this is why we use metal pans. Metal pans are made of metal. Have y'all ever heard of Revere ware? Like after Paul Revere ware? The bottom of them are copper. They actually, you could see the copper on the bottom of them, but they were really hard to keep clean, so now they put the copper in and they covered it with stainless steel, so you usually see a stripe of it right there. So you can see right here our iron frying pan, so cast iron in particular warms up really well, and one made out of earthenware, I don't know what that would be, like a crock pot? Crock pot heats up more slowly. Its specific heat is greater, so it's harder to warm that up. I will say that it will hold on to its heat. Of course, iron pan does as well. So a metal spoon, sometimes if you're stirring with a metal spoon, it'll make your hand hot because it travels through the metal spoon, where if you're using a wooden spoon, no problem, right? So that's because of the specific heat of the metal versus the wood. I think your book asks something, if I heated up a wooden pan and a metal pan, I'm thinking, who's going to heat up a wooden pan? It's going to burn up, you know, so. All right, so these are some common specific heats capacities. So I don't believe you have to write these down at all, and you certainly don't have to memorize these. These will be given to you. The only one you have to memorize is water. But it's going to be easy. Look at that number, 4.184. Does that sound familiar? Right? That's 1 joule, right? Okay. So look what we have. We have air is 1.01, aluminum 0.9, here's 0.3, 0.1, 0.4, 0.1, 0.8, 2.0, ice, look at that. Water has really, really got a high specific heat. What does that mean?
Hard to heat up.
It's hard to heat it up. And that's good news, Because if it were easier for water to heat up, it would be evaporating out there. We wouldn't have any water in our rivers and lakes. Okay, so it's good that it has a very high specific heat, but that's very high, right? It boils at 100 degrees, so it's very high, its specific heat. Okay, so just keeping these things in mind, what's the lowest one on here? Looks like gold, yeah? So that's going to heat up really quickly, and I believe it'll melt pretty easily as well, yeah. Okay, so water has a very high specific heat. Does that mean that it's harder or easier to heat up? We just answered that. It's harder to heat up. If you do not want a substance to combust or melt in your experiment, do you choose a substance with a high or low specific heat? You don't want it to burn up or melt.
The high.
Yeah, it's going to be higher. In fact, this glass right here, it's called broccosiliate glass, and it is made specifically to not heat up very much. You know what I'm saying? So it can withstand a lot of heat. It's got a high specific heat of glass. All right, so here's our first example, page 431, example 12.1. In order to cook an omelet, see, chemistry is very practical. A 5.0 kilogram iron skillet must be heated from room temperature, which is 25 degrees C, to 150 degrees C. How many joules of heat must be used to accomplish that? And our specific heat of iron is this number right here. We're going to use this equation right here. We are not going to watch this video, but I do have the answer. Here's what we're looking for. We're looking for the heat. So what in here are we looking for? What of those variables are we looking for? Well, we'll have to find T right here, right? So, but what we're asking for is Q. Yes, so that's yay. We can just put Q equals MC delta T. I've got my C right here. I've got my mass right here. So let's see our answer right there. Okay, so my joules, grams, and degrees C right here are going to talk about our units right here. So what I need to do is make sure that my mass is converted from kilograms to grams. Right here, I've got 5.0 times 10 to the 3 grams instead of 5 kilograms. My temperature in C, that's good. I just have to do some subtraction there. So my delta T is 125, right? Yes. And then my C, I'm just going to plug right in here. And I'm going to end up with 280,000 joules. It's just a simple math equation right there. Simple math. All we had to remember was to make sure that we matched up on our units, which were grams, right there. I think that's the only little hitch in that thing. And when on the video, he went on and on and on about the significant figures. So I'll accept that number right there, 280,000 joules. And I don't have to. I'm not worried about this either. I'll just put in your 5,000 there. Let's go. All right. Did everybody get everything needed for that one? You need that back. Okay. Remember, all of that is also in the book. And hopefully, in your quiz, you'll have this kind of problem because it's pretty easy, pretty straightforward. So that is our easy problem. We have two other problems we're going to do that aren't difficult. We just have to do a little more thinking about it. So our calorimeter looks something like this. It's a process that measures the heat released or absorbed during a chemical or physical change. So what can happen is, what we're going to do is we're going to take our calorimeter and we're going to put water in the little thing here, okay? It'll be room temperature water. We'll make sure that it just comes to room temperature or whatever. And then we'll measure it. They have a thermometer sticking down in it, so we'll measure that, okay? And then we'll boil some water and have some metal boiling in there, and then drop that boiled metal that's been boiling for a while into this water, and it's going to raise that temperature up. We're going to find our delta T right there, okay? So that's a really good experimental value that we're finding. So I have in our book, we're shown how to make a styrofoam cup calorimeter by putting two styrofoam cups together, but it still has the top is open, which always bothered me. My calorimeters look like that, okay? And we put a thermometer right in that hole right there. If we want to measure the amount of heat released by a substance, we can surround that substance with water and a calorimeter and measure the change in temperature of the water and the calorimeter. But we can also do a chemical reaction inside the calorimeter. okay, and measure it that way and not lose any heat. The idea is if I'm trying to measure the energy, which is the heat, it's spreading out, right? It's moving out, it's moving away. And so trying to capture all of that is difficult. That's why we end up using a calorimeter. And this is the styrofoam cup type that would be here like this. And we could do that, but like I think we might use a Yeti cup and see how that fares. Okay, so now our calorimetry equation, they have two steps to us. We have to make sure we're doing those two different steps. That's the only difficult thing, is to remember to do both steps. In fact, when we're doing the lab itself, I always have to remember to go back to that second step. Otherwise, I'm putting the wrong numbers in, all right? So the actual calorimetry equation is negative Q of the object, the thing we're measuring, equals the Q of the water plus the Q of the calorimeter. And in many, many cases, it will tell you in your book when you're doing practice problems, ignore the calorimeter, okay? So oftentimes you can just have that be 0. That's okay to do that. I think our first one, we're not going to ignore it, and maybe we'll on the second one. The minus sign just means that energy is being released. We have exothermic reaction going on. In other words, we have heat that's spreading out. And because energy is neither created or destroyed, we have to balance those out on each side, right? So we have the negative on the one side and the positive on the other side. Any heat gained by the calorimeter in the water must have been lost by the object. Negative. It's being lost by the object. It had to be because of thermodynamics. The Q for each part of the equation is to be calculated. So if you see that, the Q for each part of the equation needs to be calculated. So we have to do these two steps. All right, so we will watch the video on this, sadly. Here we go. A chemical reaction is carried out in a 5.0 gram calorimeter. The device has a specific heat of 1.95 joules per gram C and is filled with 150 grams of water. If the temperature of water was 24 at the beginning, 32 by the end, how much heat was released by the reaction? So let's watch all the steps here. I'm sorry if it goes on.
In this calorimetry experiment, we're analyzing the energy released by a chemical reaction. When the reaction begins, it releases energy, which heats up both the water and the calorimeter. The change in temperature experienced by the water and calorimeter can allow us to measure the energy released by the chemical reaction. Well, since this is a calorimetry experiment, we'll probably be using the calorimetry equation. Negative Q of the object equals Q of the water plus Q of the calorimeter. Now realize that the object here is the chemical reaction. Since we're trying to measure Q object, we must be able to calculate Q water and Q calorimeter from what's given. How do we calculate Q? Well, we use equation 2.3. Q equals mc delta T. Well, the mass of both the water and the calorimeter are given, and we know the specific heat of water. We're supposed to have that memorized, 4.184 joules per gram degree Celsius. And we're given the specific heat of the calorimeter. All we need to do then is figure out delta T. Well, since the water and calorimeter are in contact with each other throughout the entire experiment, they both start at the same temperature and end at the same temperature. So they both have the same delta T. So if we calculate the delta T for one, we'll have the delta T for the other. Now remember, delta T is defined as the final temperature minus the initial temperature, and both those temperatures are given to us. So we can easily calculate delta T. For both the water and the calorimeter, delta T is the final temperature, 32.0 degrees Celsius, minus the initial temperature, 24.0 degrees Celsius. When you subtract those two numbers, you get 8.0 degrees Celsius. What about significant figures? Well, we're subtracting, so we look at decimal place. Both of the original numbers go out to the 10th place, so our answer can go out to the 10th place. Therefore, 8.0 degrees Celsius is the proper answer for delta T. Now that we have delta T, we can start calculating Q for both the water and the calorimeter. Let's start with water. The problem tells us there are 150.0 grams of water. We're supposed to have memorized that the specific heat for water is 4.184 joules per gram degrees Celsius, and we just calculated delta T is 8.0 degrees Celsius. Now when we multiply all of this through, the grams cancel, the degrees Celsius cancel, leaving only joules. That's the proper unit for energy. And when we multiply the numbers, we get 5.0 times 10 to the 3. Now remember, we got to worry about significant figures here. 150.0 has 4 significant figures, 4.184 has 4, but 8.0 has only 2 significant figures. So our answer can have only 2 significant figures, and that's why it's listed as 5.0 times 10 to the 3. Notice that's the only way I can properly report this answer to 2 significant figures. If I had just written down 5,000 joules, that would have only one significant figure. But 5.0 times 10 to the 3 has two significant figures because of that decimal point. Okay, well that's Q water. What about Q calorimeter? Well, we use the same equation, Q equals mc delta T. The mass is given as 5.0 grams. The specific heat is given as 1.95 joules per gram degrees Celsius. And the delta T was already calculated, 8.0 degrees Celsius. When we multiply these through, the grams cancel, the degrees Celsius cancel, leaving us with a unit of joules. That's good because that's the proper unit for heat. And when we multiply the numbers, we get 78. Once again, I have to limit it to two significant figures because the mass and the delta T only have two significant figures. Well, now we have Q water and Q calorimeter, so we can use the calorimetry equation. Negative Q object in this case is the chemical reaction, equals Q water, 5.0 times 10 to the 3 joules, plus Q calorimeter, 78 joules. Now when I add these two numbers together, I get 5,078 joules. However, that's not to the proper significant figures, because we're adding, so we have to look at decimal place. 78 joules goes out to the ones place. 5.0 times 10 to the 3 goes out to the hundreds place. Now don't let that scientific notation fool you. It looks like that 5.0 goes out to the tenths place, but 5.0 is multiplied by 10 to the 3. When I multiply that decimal place by 10 to the 3, I get the hundreds place. So, the least precise number in this problem is the 5.0 times 10 to the 3 because it goes out to the hundreds place. So my answer can only go out to the hundreds place. Therefore, I had to round 5,078 joules up to 5,100 joules. Now remember, the calorimetry equation has a negative in it. It's actually negative Q object equals Q water plus Q calorimeter. Therefore, the Q of the object is negative 5,100 joules. And that just tells us that the object, in this case the chemical reaction, lost energy.
Okay, so we went through all that, but you see how it did change that final answer there with that significant figure. But I would have accepted negative 5078. Okay, for that. All right, you get it? It's not bad. We just had to do this for water in here, and we had to do it for the calorimeter in there. And remember, sometimes it actually tells you to go ahead and ignore the calorimeter. And therefore, we do still have to do it for water, and then we'll do it for whatever we're measuring, the event or the metal or whatever. All right, so this one I think might be more like the one we're going to do in lab. Okay, a 28.5 gram block of an unknown metal is heated to a temperature of 151.7 degrees C. It's then dropped into the same calorimeter as before. If the initial temperature of the H2O was 22 and its final was 24.2, what's the specific heat of the metal? And I will say, look at that very small change in temperature. That's about what's going to happen during our lab. Something very small like that, nothing super dramatic, sadly. All right, so let's watch again. Try to stay awake.
Here we have another
I've got a special
calorimetry
treat
problem.
for you in just a minute.
A hot piece of metal is dropped into a calorimeter. Since the water and the calorimeter are colder than the metal begins losing heat to the water and the calorimeter. This causes the metal's temperature to decrease and the water in the calorimeter's temperature to increase. Well, since this is a calorimetry problem, we should use the calorimetry equation, negative Q object, in this case the object is the metal, equals Q water plus Q calorimeter. Now the idea here is to calculate as many of the Q's as possible so we can solve for the remaining one. We calculate Q using equation 2.3, Q equals mc delta T. So we have to figure out what masses we know, what specific heats we know, and what delta T's we know. Well, we don't know the specific heat of the metal, that's what we're trying to figure out. But we do know mass, specific heat, and delta T for both the water and the calorimeter. So we can start by calculating their Q's. Well, the mass of both the water and the calorimeter are given. The specific heat of the calorimeter is given. You're supposed to have memorized the specific heat of water. So in order to use Q equals mc delta T, all we need to do is figure out delta T. Now, as is the case with all calorimetry problems, the water and the calorimeter are in constant contact throughout the entire experiment. So they start at the same temperature and they end at the same temperature. Therefore, for both the water and the calorimeter, the delta T is the same. It is simply the final temperature, in this case 24.2 degrees Celsius, minus the initial temperature, in this case 22.0 degrees Celsius. When we subtract those two, we get 2.2 degrees Celsius. Now we're ready to calculate Q water and Q calorimeter. Let's start with Q water. We take the mass, 150.0 grams,
That was from the
times the
previous
specific
thing.
heat, 4.184 joules per gram degree Celsius, times the delta T, which we just calculated, 2.2 degrees Celsius. When we multiply all those out, the grams and the degrees Celsius cancel, which is good because the unit joule is the proper unit for heat. And multiplying the numbers works out to 1400 once you take into account the fact that 2.2 has only two significant figures. Now let's do the calorimeter. We take the mass, 5.0 grams, multiply by the specific heat, 1.95 joules per gram degree
From the
Celsius,
previous
and
problem.
multiply by delta T, which once again is 2.2 degrees Celsius. Once again, when we multiply through, the units cancel except for joules, and that's good. And the numbers work out to 21 once you realize that 2.2 has only two significant figures. So now we can use the calorimetry equation to determine the Q of the metal. Negative Q object equals Q of the water, 1400 joules, plus Q of the calorimeter, 21 joules. Now when we add these, we get 1421 joules. However, look at the significant figures. 1400 has its last significant figure in the hundreds place. 21 has its last significant figure in the ones place. The least precise number then is 1400, so we can only report our answer to the hundreds place. So our answer is 1400. Since there's a negative in the equation, the Q of the object actually becomes negative 1400. But notice what happened. Q of the calorimeter didn't matter. Why? Well, because of the significant figures involved, the calorimeter simply did not gain enough energy to really matter in the equation. So in this case, we could have gotten the same answer if we had simply ignored the calorimeter. This actually happens every once in a while in a calorimetry experiment. The calorimeter gains so little energy that it simply doesn't matter in the calculation. As a result, some of the calorimetry problems you'll do in this course will simply tell you, ignore the calorimeter. In that case, you can simply assume that Q calorimeter equals 0. All right, so now I know the Q.
So that also means that our calorimeter was good, right? Our calorimeter was a good one.
I also know the mass of the metal, it was given in the problem, and I can calculate delta T. So I have Q, M, and I can calculate delta T. So the only thing I'm missing in equation 2.3 is the specific heat, so I can solve for it. Calculating delta T isn't so bad. I'm given the initial temperature of the metal. Now remember, the metal starts out a lot hotter than the
This is
water
the
in the
trick right here.
calorimeter. So its initial temperature is not 22.0 degrees
100.
Celsius. It's given. The initial temperature is 151.7 degrees
151.
Celsius.
100 when we
What's
do
the
it.
final temperature of the metal? Well, once the metal comes into contact with the water and the calorimeter, it begins exchanging energy with them. The energy exchange ends when the temperature of the metal is the same as the temperature of the water and the calorimeter. So the final temperature of the metal is the same as the final temperature of both the water and the calorimeter, 24.2 degrees Celsius. So for the metal, the delta T is the final temperature, 24.2 degrees Celsius, minus the initial temperature, 151.7 degrees Celsius, which is negative 127.5 degrees Celsius. Okay, before we go on, I want to summarize what we've done so far. Using the information given in the problem, I calculated Q for water and Q for the calorimeter. I added them together and took the negative in order to get Q of the metal. All right? I also just figured out the delta T of the metal. So if I summarize, here's what I know about the metal. For the metal, I know that Q equals negative 1400 joules, delta T is negative 127.5 degrees Celsius, and mass is 28.5 grams. Notice that's everything in equation 2.3 except for the specific heat. So I can use algebra to rearrange equation 2.3 and determine the specific heat. When I do that, I find out that specific heat equals Q, negative 1400 joules, divided by both M, 28.5 grams, and delta T, negative 127.5 degrees Celsius. When I work all this out, I get 0.39 joules per gram degrees Celsius. I have to limit myself to two significant figures because Q has only two significant figures. So my answer is 0.39 joules per gram degrees Celsius. If I look at table 2.1, this is the specific heat of copper.
All right, so that's what we're going to be doing for our lab next time we get together. Okay, so blanks to fill in?
Just an on your own.
And on your own? Okay, I don't think I do it, yeah. So, all I had was Professor Dave's deal here, which was exactly what we just did. So we don't need to do that, all right? So we're actually finished with notes, but we're not done yet. Okay, so I have something for you. So it turns out that yesterday I got some steak delivered to my house, some steaks. And guess what was keeping it cold?
Ice.
Dry ice. So I have dry ice. It's not much, because it had to spend the night in my cooler, right? So I've got that much dry ice. It's pretty good, right? So we're gonna mess around with the dry ice just a little bit, because I have it, because I can't buy it anywhere. I had to order expensive steaks, just for y'all. No, actually, it was a coincidence, so. All right, so I'm gonna bring around some water for your beakers. And we're just gonna take a look at some dry ice. Okay. You all should be wearing goggles right now, so be safe, please. And I need gloves. So, what is dry ice? Do y'all know?
H2O.
Nope. It's not H2O.
CO2.
It's CO2 that's been frozen. Yeah. Okay. And remember the word sublimate? The word sublimate? So I'm going to take this out of its bag. So it's so cold that it'll burn your hands, okay? So you can't touch it. Okay, but notice what's coming off of it. I'm gonna put some in the beaker. Maybe I ought to put it. Let's just put it on the table for now. Guess what? It's not gonna melt and leave a puddle on our table. Because it's not melting. It's sublimating. So remember what sublimating means? Let's pick these. See how much I can break of this. Listen, it's making noises. I just have to make them small and just put it to your beaker. Should have brought them in. I'm just gonna take the table off. Oh, still got 'em. Shoes. Oh, it won't hurt you. Won't make you wet. Okay, so just take a look at it. So what's coming off of it there?
CO2.
Yep. Mm-hmm. Okay, so there it is. And the thing about CO2 is that it's heavy. So watch what it does. So it's gonna go down, right? It's gonna sink down. Because it's heavier than air. If y'all ever been to like a haunted house or whatever and there's the smoke all over the floor, yeah. If you put this on the floor in some buckets and stuff, it'll leave this kind of cloudy, cool thing on the bottom of the floor right there. Alright, so now we're gonna go ahead and put it into the beakers. Y'all can't touch it. Don't touch it. Y'all need that. Let's see, is this too big for your beaker? Yeah, I guess if you worked really quickly, you could do that, but, I mean, cause I'm already feeling pretty cold through these. Alright. So we're gonna just speed up this sublimation reaction real quick, okay? By adding a little water to it. Now, it's not going to melt, right? It's just gonna go straight from a solid to a gas. That's sublimating. And so this is just warm water, I mean, I say it's warm room temperature water. It's just gonna make it speed up more quickly. And so you're gonna see how it's gonna start going. So what those bubbles there,
Oh, that's not even water. Wait, whoa.
so you may think, oh, I'm boiling the water. Actually, it's gonna end up making your water really, really cold. Alright, so there, notice how it's sinking down because it's heavier. So this is also, all that's doing, y'all, is just increasing the rate of the sublimation. That's all that's happening right there. Now, some people have asked, well, could we put it like in a punch? You know, and make your punch really cold? So the answer to that would be yes, but you don't want to get that in your cup. You don't want this to go in your, you don't want the CO2 to go in your mouth. It'll burn a hole right through your esophagus. Okay, you don't want that to happen. All right, that's bad news. Okay, so there's this really cool thing that this does. I have a plate here. Because it's so cold, if I put water on it, the water freezes immediately.
I'm controlling.
And so I'm going to use a colored water. So you can see it better. I guess that's flat enough. So you see it's kind of flat there. And if I put a drop right on it, it's going to freeze this little drop. It's going to, when I say freeze it, it's going to keep it kind of in it. It's not going to solidify completely, but it won't stay. So it's just going to, it won't absorb into it. Usually it rolls off. Oh, see, it rolled right off. Yeah. All right. Try to put this over here without it rolling off. See, so there's just that little blue. And it doesn't sink into it, you know. So I'm thinking if that one stays on there long enough, it'll actually turn into a little solid ball right there.
So funny.
So it's just beautiful. Yeah. So this guy.
Oh, cool. Okay, that's cool.
Maybe it's actually frozen. Oh, it is.
That was fast.
Yeah, so it didn't take long. Oops, it's on there. Okay, all right. So what we can also do is, let me put the going here. Of course, this is just fun. You had younger siblings or something, and if HED ever starts carrying it again, a little birthday party doing this with some cool, you know, flask. I think I have a flask over here. So we'll put a different color on this one. How about red? Because we can. Remember the other two? You're gonna use red. Or anybody. All right, let's just swallow it. Don't swallow it.
That is so cool. I love how cold it is. It looks like metal.
And now if I had hot water, this is not hot water. I couldn't get that sink in there to go hot for me. So you see, I'm just gonna have some cool looking stuff. So my kids at one point, they were doing a 4-H project for photography, and we had a bunch of different colors and a bunch of different shaped science glass, you know, some long tube necks and this kind of stuff, and they took a photograph of it in the dark with flashlights underneath each one of it, and they ended up winning a
Oh, cool.
contest, a photography contest, because it was just unique, you know, it was something that other people weren't doing and that kind of thing. Now, the other thing we can do is if I take this right here, maybe that's too much water. Because I can end up with this thing making a mess if you get a lot of ice in there. So the reason why it stopped doing that is because it got so cold, the water got so cold, that the sublimation just went back to its regular rate. You couldn't see it as well. So I'm going to take this large thing here, and let me be right back. I gotta go across the hallway real quick. Alright. It's a bit of soap. So the soap, the bubbles will be captured. I'm thinking this is just, it's very lovely smelling. It does say soap with essential oils. Okay, let's stir that up just a bit. Alright, and then I'll go ahead and use this plate just in case. So we're still just gonna have, it's just the same deal, sublimation, but because I have the bubbles in there,
Oh, cool.
I'm gonna end up trapping the CO2 in the bubbles, and then you can just go like this, and there's your CO2. So the guy did that in the video. Alright, so y'all can do that if you want to. You can touch the bubbles. That's not a problem right there. All right. So, and what the only thing else we would have done with this in our gas lab would have been to put like in a big bowl and try to make a big bubble, which I fail at every time anyway. So, bring another plate. I guess I'll just clean it. Does it feel cool when you touch it? It should feel like slightly cool. And then, but now what would happen if I put food coloring in this one? Any predictions?
Colored bubbles.
Would they be colored bubbles? What do y'all think? Or there's certainly colored bubbles where it hit the blue down here. Trying to get it down. Well, I colored the bubbles. I actually just inserted it into the bubbles. Let's put some soap. There, I got it in there so you can see it. Let's put some soap in here. And if it slowed down, like for instance, this one that slowed down so much because your piece of ice was so big, if we added warm water to it, it would increase it. Okay, there's some bubbles coming. So I'm trying to see, those bubbles shouldn't be blue. Because the gas, so I think it's only green here because, is it making your hand green now?
Yeah.
Sorry about that. Yeah, if I put this food coloring in first, then it shouldn't have made those colored bubbles. I just added it to it, yeah. So yeah, let's try to keep the food coloring from getting on that. There we go. Alright, so there's our dry ice, y'all. So at least we had it. Sorry I couldn't have it in a lab time. I'll still do it if I can get it, if I can find it. I'll order more steaks, I guess. Alright, so that's it. You have the week off for spring break. You can touch the bubbles on your way out if you want. But when you get back after spring break, you will have a quiz and we'll do the lab over this, okay? So take a break, study next Monday week, right? Monday week. And happy spring break, everyone.
Thank you, Mr.
You're welcome.
So fun. Thank you, Ms. Casper.
You are welcome.
Do you have my quiz or do you want me to get it when I come back?
I'll need to put it into
Oh,
the
okay.
computer to give you the extra credit on that.
Okay. They told me to come look at your soap and dry ice. That's so now my hand is blue.
And you touched it too soon.
Yeah. Henry. That's so cool. So if the soap wasn't in there,
It would just be doing like
it
how
would
these
just
were
be
doing.
just
Yeah,
smoking?
just like these, just like that. So it gets captured, it gets captured in the bubble.
That's so cool.
Yeah, so I'm gonna actually take this to the kitchen.
You want some help?
Well,
Is it frozen to the